So moving right along to the next section, this one is all about Hooke's law. So what are the purposes for today? We're going to understand what elastic forces are, which relates to Hooke's law, and then we're going to solve some problems involving Hooke's law. Here we go. An elastic force is a force that is working towards returning a distorted object to its equilibrium or rest position. So this is a complicated word definition of basically, if I take a spring and I stretch it, there's a force that wants to return it to its original position. Or if I take a spring that's this big and I squish it, as soon as I let go, it returns to its original position. So that's what elastic force is if I distort or change the shape of an object, there's a force that wants to return it back to the original form. So this only applies to certain objects because some of them, if you pull them apart, they don't want to move back to the same position. Elastic forces only apply to certain objects. Some examples for this, you've got elastic bands, springs, trampolines, bungee cord, bouncy ball. So Hooke's law states that the amount of restoring or elastic force is proportional to or changes the same amount as the distortion. So the more I stretch a spring apart, the more force is required. So as I start pulling, it's easier, then it gets harder and harder and harder to pull it apart because it requires more and more force. Many of you have ever shot a bow and arrow before. The farther you pull back on the bow, the more force you need to pull it back. So the equation for this is Fe equals K delta X. So the triangle is what's called delta. Let's go through what each of these things are. K is the spring constant. The units for that are newtons per meter. And this is constant per object. So one spring will have the same spring constant. K is stating how stiff the spring is. So the bigger the K value, the harder it is to pull that spring or bungee cord. Delta X, so this is all one thing. The delta just means change in. You've seen that with kinematics, change in displacement, change in velocity. And this is just what's the distortion from equilibrium. This is a length, its units are meters. So here's an example. We've got Legolas is shooting a bow and arrow, and if the spring constant is 80 newtons per meter, and Legolas draws the arrow back 20 centimeters, we want to know how much force is he applying. Here's our equation, Fe equals K delta X. We have the spring constant. We have the distance, but notice it's in centimeters, so I had to convert it into meters. There is our force elastic. That is a really easy example. So if we've got a 30 kilogram koala sitting on a branch and it bends the branch by 1.2 meters, we want to know what's the spring constant of the branch. Let's first look at what a free body diagram looks like to figure out what forces we're dealing with. So the koala sitting on the branch, it has force of gravity pulling it down. The branch is applying an elastic force up because the branch bends. And since it's just sitting there, these two forces are balanced. So that tells us our force elastic is equal to Fg. So then we can plug in numbers since Fg is just mg and solve for K. Another example here, we've got a 80 kilogram person being shot sideways in a human slingshot. I don't recommend it, but you can try it if you want. So that slingshot has a constant of 15.2 newtons per meter. If the slingshot was stretched by 30 meters, we want to know the initial acceleration. So in order to do that, we need to first look at what's our Fe. So Fe is change in delta X. We know those numbers. We have force elastic. But how does that relate to acceleration? Well, F net is equal to this Fe, which is equal to ma. And we know the mass. We know Fe. We just solved for that. So we can solve for acceleration. So let's do another example here. This time we've got a spring. It's compressed from 42 centimeters down to 10, and you're given the force there. We want to know what's the spring constant. So we're using the exact same equation, except this time we actually need to calculate what's the change in X. So I went from 42 centimeters and I squished it down to 10. So we want to know what's the difference between those. And again, we're converting from centimeters to meters. So we can get this as our K value. So there you go, that's Hooke's law. It's dealing with elastic forces. So anytime you're dealing with a situation where an object is changing its shape, you're going to deal with a spring or a bungee cord or something that is bending or expanding. You're going to deal with Hooke's law. All right, kiddo, we're going back to the Incredibles again.
Okay.
So here's this one. See if you can see what is not possible. All right?
Sure.
Okay, here we go. What do you think about that one?
I don't think he can lift the trucks.
You don't think so?
No.
How about this part? Where he can lift up the whole train.
No, that can't be good.
How come?
Because he should there must be the same balance because it doesn't. It's not in the middle.
Oh, he has to be in the middle?
Yes.
Oh, yeah. That's a good idea. Yeah, because what would happen if he's not in the middle?
The one with the heavier side would go down.
Mm-hmm. What about this one?
That part he couldn't jump.
No, he can jump like that.
Yeah.
How about this part? Do you think he can do that?
No.
How come?
Because it's too heavy.
He'd have to be really, really, really strong.
Yeah.
So his name's Mr. Incredible. He's supposed to be really strong. So maybe, do you think a superhero could do that?
Superhero.
If he was a superhero?
Maybe.
Maybe. If he was really strong?
Yeah.
But could a person do that?
No.
Could you do that?
Nope.
No. How about Zoe?
Not at all.
Oh, okay. Mateo?
Nope. Not at all.
How about Bubba?
You would have to be much stronger.
Much, much stronger. Yeah, I'm not that strong. There you go. There's that one.